Students, welcome to lecture number 37. So, we have been discussing about the error analysis in machine learning and the score. In addition, we are going to talk about or start discussing about the material informatics, a branch of AIML which is very new. So, we are going to start discussing about that. Then we can continue discussing all these aspects of material informatics in lecture number 38 to 40. So, that is the main discussion today. We are going to take material informatics as a starting point and carry forward. But in the meantime, I remember in the last class I could not finish discussing about the some amount of data preprocessing, especially error analysis and a model score, which will do that. But before that, let us see what we have learned, because that will set the tone of the next part of the lecture. Data preprocessing means we want to ensure good quality data, right? That is what is the key thing, because in machine learning and deep learning we are dealing with data. Data is our most important entity. In handling data, we need to take care of quality of data. That is the key aspects of any kind of modeling you want to do. So, quality of data is what is to be ensured, and what are the major tasks if you want to ensure good quality data. You need to clean the data, you need to integrate the data, you need to reduce also the data. Sometimes it is dimensional reduction, sometimes reduction in terms of the volume of data, and lastly you also need to do data transformation and data discretization. These are the four aspects which are actually major tasks in data preprocessing, but there are many others which will come as we start discussing about that. So, first we talked about this, what ensures the data are of good quality. Okay, so, data basically can be considered good quality if we ensure following measures. First, accuracy. How good the data are will be dictated by the accuracy of the data. It is not about correct or wrong, it is about accurate or not accurate. That is the important aspects. And by accuracy we means high accuracy, low accuracy. Everything is in terms of that. And secondly, we also need to know that whether data are complete or not, because we cannot handle incomplete data. Why? Because you cannot get a good prediction of the model by using incomplete data. Completeness means it must be available. It is very important to have available data. Okay, that is the key aspect which you have to understand. Without ensuring that, we cannot say that data is good quality or not. Please remember that availability of data is in terms of completeness is a very key important aspects. Similarly, consistency. Many times there will be some modified data, but some are not, and that is a part of the data analysis. But if you do modification, you have to do it completely to maintain the consistency. Sometimes you have data which are available today, but may be available after some times. So, because of the time aspects, we need to have updation of the data, that is called timeliness. And the last two factors which are very difficult to quantify, let me tell you. First is the believability. How trustable the data are? That is the very difficult question to answer. And last one is the interpretability. How easily data can be understood. So, these two factors are very difficult to put a measure of these two aspects. Many times we simply say yes, we have got good, accurate, complete, consistent data in a timely manner, but we are not sure about whether they are believable or not, they are interpretable or not. That is why last two factors are very difficult to quantify. So, these are the things which will quantify the data quality is good or not. So, what are the tasks we have to do? First is obviously we discussed about, you have to clean the data. And what do you mean by cleaning data? Fill in the missing values. You may have smooth noisy data, you may have to identify or remove the outliers or resolve the inconsistencies. So, missing data, what is very important to fill up, without that you cannot complete it. Many times you may have noisy data or you may have outliers. You will plot and see that outliers are very clear, that has to be removed, and sometimes you need to also resolve the inconsistency in terms of data. So, integration is very important in terms of material science engineering. We may need to integrate multiple databases, like in thermodynamics, which we will discuss today. There are different types of databases available, files available. How to integrate that? That is also key aspects in data preprocessing. And as I said, data reduction, it means three things. Data dimension reduction, this aspect we have discussed in deep learning and machine learning, especially in deep learning quite a lot, that whenever you have large amount of data and you want to process it for a model, first thing is to do is the dimensional reduction. What is that? Well, you understand that you have n dimensional data, that means there are n variables, and corresponding to each variables you have level. So, that means it is like a huge data. So, now we have to understand how many of these variables are independent or they are not related to each other. Sometimes it is difficult to do that, sometimes it is difficult. Why? Because you have a large number of variables, but still using different approaches of machine learning and deep learning, we must be able to do a careful analysis of that and do a dimensionality reduction. That is called reduction. Other than that, you can also have numericity reductions and data compression. Data compression is corresponding to what? Corresponding to images. You know, when you are talking about image, I discussed it also. The images are normally very big, but images are digitized, and images are digitized in a specific way. Therefore, you create a huge amount of data. There you need to compress it. There are few models actually, especially deep learning models, which compresses the data like autoencoder. And last thing is the data transformation or data discretization. Transformation, we mean normalization. Many cases it is very important to normalize the data with respect to the highest value or respect to something, some functions also. That helps us to keep the data in one standard, otherwise we will have problems of normalization. But you also have a hierarchy generation. Hierarchy we know, right? In case of decision tree we have discussed about hierarchy. Hierarchy means how the data has come from, whether there is a parent product relationship or any kind of other relationship possible. That is also required for data transformations. So, these four aspects, data cleaning, data integration, reductions, transformation and discretization, they are the major task when you want to preprocess data, and you will all do that, because most of you when do a machine learning or deep learning model, you will find whatever data you are using will have this kind of problems. They are not truly easily manageable. I do not want to go in details of this, we have discussed about it a lot in the last lecture. Data cleaning means you need to have in completeness, consistency, you have to ensure, and also you need to also remove the noise data. You know, many of these experiments generate a lot of noisy data, like X-ray diffraction. The peaks are sitting on a background. If your background is not properly adjusted, you have a noisy peaks. So, noisy data are common to material science, whether it is X-ray diffraction, whether it is a scanning electron microscope, EDX measurements, or whether it is a calorimetry measurements, you will have lot of noise, and this noise has to be, or noisy data has to be cleaned. That is the key aspects of that. So, there you have to find out what is the noise and how this noise is affecting the error and what are the outliers. Inconsistency, I already talked about it. Inconsistency is very common when you talk about data. Many cases you can also have intentional problems like disguised missing data, that is also possible. So, these are the aspects. Now, many times we will find that data is not available for some instances, that leads to data incompleteness, and this can be due to machine malfunction, due to inconsistency with our recorded data, therefore deleted, not entered because of the misunderstanding of the experimentalist. Okay. If experimentalist is not a very serious person, he may or she may misunderstand and remove the data. Certain data may not be considered important at the time of experiments. This is something which always happens to many of our students. They believe that this data or this category image or this X-ray diffraction plot is not important. So, they simply do not enter, and many times you do not register history or change of data. You might have changed the data, but you have not entered the date when you have made it change, why you have made it change. So, missing data needs to be therefore inferred, and that inference is a big problem. The moment you infer data, you are making some kind of compromise in terms of the quality of data, and that is why you have to do a lot of things, like you have to ignore the tuple, and this is basically done when the class level is missing, not effective when percentage of missing values not per attribute varies considerably. By attribute we mean the features. Fill in the missing values manually, well that is I do not know, that is very tedious and many times infeasible. Sometimes it is possible to do automatically if you have some attribute mean, if you have some standard deviations or you have a global constants, or many times you can also do like most probable value, that also possible. You can use inference Bayesian approach or decision tree approach to do that. For noisy data, it is a random error and it can be attributed to faulty data collection instruments, that is what I said in X-ray diffraction, maybe problem of data entry or data transformations or inconsistency in naming or conversions. There can be also duplicate records, incomplete data, inconsistent data, all these are possible. This can lead to noisy data. And in order to handle this, you have to do either a lot of things. You can do binning, regression, clustering, or you can do both combination of computer human inspection. Binning is the best method. First sort the data and partition into bins, and then you can smoothen bin means smooth by bin median or bin boundaries. There are many techniques available in statistics. Regression is obviously one of the best way of handle noisy data. You can do clustering also and detect and remove the outliers, and if you cannot do any of these three things, you can always combine computer human inspections. And data in discrepancy detection is big problem, you cannot easily detect it, and many cases fields are overloaded, you have problem of uniqueness, consecutive rule, and that is why you have to use some kind of a commercial data softwares like data scrubbing or data auditing. These are available. You can use simple domain knowledge to data scrubbing to detect errors and make corrections. You can also analyze data or discover rules and relationships to detect violators, but these are possible when you have good knowledge of the data. Many cases you can integrate the data or migrate it, like data migration tools. It can allow transformation to be specified. You can also use extraction or transformation or loading tools also. Integration means you have iterative plus iterative process, both the things possible to integrate the data. Since we are talking about integrations, integration means combination of data from the multiple sources into coherent source. There are a few ways to do, like one is schema integration. This is like A cast ID equal to B cast something, this integrate meta files from different sources. It is done quite frequently in thermodynamics databases. You can integrate different meta files. You have a source file from nickel based alloys, you have a source file from iron based alloys, you can integrate these two and get a database of nickel and iron. You can also do entry identification problem, like multiple data sources may have problems like that. Give example is Bill Clinton is William Clinton, we know that both are same names, but written in a different way, so sometimes it can lead to identification problems. Detecting or resolving data values actually can be conflicting also. From real world entities, like attribute values from different sources are different. So therefore, you can have different representations or scales, like matrix or British units, there are different scales. So all these can lead to problem of resolving the data conflicts. That is why integration of data is sometimes problematic. If you have a data from British system, APS system, you have data from CGS system, first you have to convert it in one system and then integrate it, right. You can also have different attributes for two sets of data, different features, different variables, how to integrate them. These are problems you will face always when you try to integrate data. So, that is why it is better to use schema integration, or you can always use same kind of files to join. Another important aspect you will see in data handling is called redundant data. You can have redundancy coming from object identification or derivable data. Derivable data is very common. One attribute may be derived from another attribute, like annual revenue from the revenue table. You have a revenue table monthly, then you calculate annual revenue. So, you have a derivable data that can lead to redundancy. Redundant attributes may be also able to detected by this correlation analysis, that is called, or covariance analysis, that is called R square analysis, which we will discuss in the error analysis, or we can do careful integration of the data from multiple sources, that is also possible. But it can also lead to problem of inconsistencies. So, you have to be careful about how to integrate that. There are many ways one can do correlation analysis. One is a chi-square test, we talked about it. Larger this chi-square value, more likely the variables are related. So, therefore, we can actually remove data which are similar related variables and get a consistent data. Like in a hospital, if you want to, example is that number of hospitals and number of car theft in a city do not look like correlated, but both are linked with population. Higher the population, higher will be number of hospitals and higher will be theft of the cars, right. So, these cost correlations are possible, and that can be done using either chi-square or you can do a correlation matrix like Pearson product movement coefficient, and this is very simple. As you can see here, n is the total number of variables or total number of data rather, and ai is the type of data and bi also, and a bar is the average of ai type of data, bi is the average of, so ai is one type of data, bi is another type of data, a bar is the mean of ai and b bar is the mean for that. Sigma a is standard deviation, sigma a, sigma b is standard deviation of that. So, now we can define the Pearson product movement coefficient like that way, summation over ai minus a bar multiplied by bi minus b bar divided by n minus 1 into sigma b. If RAB is more than 0, then a and b are positively correlated, and higher the value, stronger is the correlation. And these correlations are very important to understand, because if two attributes are heavily correlated, strongly correlated, you can ignore one attribute and take out the values of those attributes and go for the machine learning model. But if it is not less strongly correlated, like it has the negative values or small values close to 0, then they are not correlated at all. So, negative correlation and the independent ones, that is what you can ensure by this correlation analysis. This will be key for material informatics also. Well, in terms of reduction, data reductions can be, what is that? It is basically, as I told you, it can be dimensional reduction, numerical reductions, or compression, right. And we want to do this in why? Because we may not be able to store terabytes of data, and because you need a lot of memories, and many times if you do a complex data analysis, it might take a very long time to run on the complete data sets. That is why you need to do reduction, and first reduction strategy is dimensional reduction. What is that dimensional reduction? It is remove the unimportant attributes. As I told you, you may have a large number of data, right, from different attributes, different variables. We need to ensure which variables are correlated to each other. If we can remove the correlated data, we can do a lot of dimensional reductions. That is done by principal component analysis. Anyway, this we have discussed. We will discuss again about this PCA more when you talk about the material informatics. You can also do feature subset subselection or feature creations or wavelet transformations. Okay. Please read all these things. I may not have time to discuss each of these, but PCA is definitely one of the major tool for dimensional reduction that can be done. Whatever numericity reductions, some people call it data reduction, is basically regression or log linear models. You can use histograms, clustering, sampling, or even data cube aggregation, that is also possible. Basically data cube means you create a cube and you can aggregate the data into that. Same is like a clustering. Histogram is another way, you know that. And lastly, you can do data compression, that is nothing but compressing the data. You have an image which will have a huge size of data, we can compress it. We always do file compression, right, in computer. So that is what is called data compression. Well, then we also discuss about some error analysis, but at the end we stop it because of time constraint. Error is very important, right, it is a very vital to important to diagnose the error, and it is defined as the difference between predicted value and the actual value, remember that. This is can be observational measurements. We can determine model performance, identify areas of improvement also. We can determine also insight into the quality and relevance of the data, complexity of the problems, effectiveness of the feature engineering and model selection. That is why error analysis is very important, and by error we mean difference between predicted value and actual value. And how we do that? This is what we need to recognize this source of error, assess and enhance the model performance, and also maintain the model relevance. But there are different types of errors. First one is to discuss is the mean absolute error, right, and that is nothing but what? That is nothing but it is basically, let me go back to the board and discuss about it. Is ME is means of absolute error, is basically means of absolute, it is a measure of average size of the mistakes in a collection of predictions without taking their accounts. So mean absolute error, that is what is called MAE, that is equal to 1 by n sigma I 1 to n. Okay. So I think it is yi, am I using yi? Yes, yi, yj, sorry, not I, j. So this is also j minus. So this yj is data at any instant and yj cat is the average. Yj's. So what you are summing up? Well, you are summing up the difference of this each data and the mean or average. Okay. So let us write it as a mean. Mean is better. Mean. So you can see that. That is what is called. This is actually absolute error. Remember. That is why you are dividing this way. From each data, we are subtracting the mean, and whatever difference we will getting, we are summing it over, and that dividing by the total number of n is the total number of data, right. In a data set, you can have thousands of data, right. That is what is called MEA, the mean absolute error, and this is very important. It basically provides, it is more widely used for regression analysis, but it can be used for other possible also. It provides you resiliency to multiple errors. It can also give linear score. It is very straightforward. It is used all kinds of disciplines like finances, engineering, microbiology or meteorology, whatever, and it provides information of the size of the error. That is the key thing. What is the size of error it can provide? Yj minus y cap j, that is what is giving you the size of the error. One can also do mean squared error, that is nothing but a square, same thing we are squaring, that is mean square error, that is the same thing we are squaring. Squared it is same thing, okay, 1 by n j 1 to n yj minus y cap j whole square. You can see that we are basically instead of absolute error we are taking mean squared error, and this is the square term. That will make sure that there is no negative. It is computed by calculating average, especially the mean of the squared mistakes, mean of the square mistakes resulting from the functions data or any actually data, and this is a measure of error in prediction algorithms. Statistics quantifies the average squared variance between observed and the predicted values. When there is no error in the model, MSE will be 0, because yi minus yj y hat will be equal to 0. A model what increases in proportion to the degree of error it contains. Average square error is often or many times called as MSD, mean square error, average square deviation actually. This is also very important, because it provides you the insight of the model performance, this error. Then we discuss about R square. I want to spend a little bit more time on R square today, because something I forgot to tell you this. R square is what? It is basically a measure that provides information about the goodness of fit. Remember this, goodness of fit, all of you do that, and look at this definition of R square which is given, and this is in context of regression. So, R square is like this. It talks about goodness of fit. Am I clear? So, that means that is equal to 1 minus sum squared, sorry, 1 minus, let me write down that, 1 minus yj by yj cap whole square divided by, this is obviously j going to 1 to n, and similarly this is also. So, let us say that x I is the predicted value. Okay. So, I write here x I is the predicted value. Since I changed the expression, that is what. So, I was looking at the wrong paper, predicted ith value, and y I, sorry, x j, let us say y j is basically actual ith, this should be jth actually, not ith, jth value. So, one is the predicted value by the model, other one is the actual value which is obtained. So, now we can always consider mean as a y bar that we have already told about it, that is nothing but 1 by n summation I 1 to n y j, sorry not I j, j 1 to n y j, okay, that is the mean. So, now we can consider this R square as like that, we know this, then R square will be this 1 minus ratio of two terms summation j 1 to n x I or x j minus y j square, and then this one is different. This is equal to j 1 to n y bar minus y j. That is the problem of this, let us be very clear about it, y j whole square. This is what is called R square. So, you can see R square will be equal to, now we can also define a term called means MST. What is that? Mean total sum of square. Mean okay. Let us write down all the terms. Mean total sum of squares, and that is equal to 1 by n sum j 1 to n y bar y j whole square. Is it y bar y j? no, it is not, this is wrong, that is what I was thinking. This is yj by y bar. So, this will be also yj by y bar. Please correct it. This expression is yj by y bar. So, this difference is basically what? Between the predicted jth value minus the actual jth value, and this is the predicted the actual jth value minus the mean. Okay. So, therefore, this is what is called MST. Now, if you look at carefully, the top one is basically MSC. So, therefore, R square is nothing but 1 minus MSC divided by MST. So, once you get both these things MST and MSC, you can easily find out R square. That is what is R square is. Please take a note of it. R square is that. Okay. So, these three aspects, one is called mean absolute error, other one is called mean square error, and third one is R square. They are the main errors in the things. There is another error which is called roots mean square error. That is nothing but this. We are taking a root of the MSC. Okay, whatever MSC is there, we are taking a root of that. You can see that this one is root of the mean square error and nothing else. And machine learning, it is extremely useful to use, because there are a large number of models to judge, and you have to calculate these errors to know which model is working better than other things. In addition to that, there is another error called mean percentage error. Okay. That is nothing but very easy to understand, that is percentage, say 1 by n into 100%, and this is the t, at is basically your value of the what is called the predicted value, and ft is the original value. Here at is the predicted tth value and ft is the actual tth value. And you see, you are taking the difference between them, dividing by the predicted value, sum it over and then take a percentage. That is also some time used. This is called mean percentage error. So, these are the errors we have discussed about it. The last one is called log loss. It is a crucial matrix in machine learning, particularly in classroom classification problems. It is the evaluation measure to check the performance of a classification model. It measures the amount of divergence of predicted probability within actual level. It basically measures the amount of divergence. The lesser the log value, more is the perfect model. So, how do you define? Log loss is defined like this, is equal to minus 1 by n, sum it over I to n, j I to m, x I j into log p I j, where n is the number of observation, x I is the actual binary outcome. Binary means 0 or 1. How do you know? If it is correct, it is 1, if it is incorrect, it is 0, and p I j is the predicted probability that one observation belongs to class 1, not 0. So, basically you have to have a probability distribution also. It is very difficult to compute, let me tell you, log loss. Although this tells this is a very good measure upon certain your divergence of a predicted probability, but it is not easy to measure. Many cases you will find calculating log loss is a big trouble for you, because you do not know what is the how this probability distribution will look like. So, that is about the this thing. So, we will stop here, and the next part we will discuss a little bit about model score and start our discussion on the material informatics.